Hey everyone, and welcome! Get ready for a deep dive into a topic that I'm super stoked to explore with all of you. Quantum physics. I know. It's got this rep for being like crazy complicated, but trust me, we're going to break it down and uncover some seriously cool stuff. You guys sent in some really interesting sources about this, so let's get right into it.
And you're spot on about that crazy complicated part. Quantum physics can definitely seem intimidating. But one of the sources actually addressed this head on, saying, and I'm paraphrasing here, it's not about, being a math whiz, it's about grasping those mind-blowing concepts.
Exactly. It's about wrapping your head around the ideas themselves. And get this, it's not like it's all figured out either. One of the articles even mentioned that its interpretation is still controversial, which I think just makes it even more intriguing, wouldn't you say? It's like
Right.
we're diving into a realm where even the experts are still like debating the finer points.
Absolutely. And that's what makes this field so captivating, this idea that we're still piecing together the puzzle. But at its core, quantum physics is all about how things work differently at the smallest levels. Think about gas atoms. On a larger scale, they seem to act like, well, tiny little balls bouncing around following those classical physics rules we're all familiar with. But zoom in closer, like way closer, to their internal structure, their energy levels,
Mm.
how they interact. That's where those quantum rules really take over.
So it's like there's this hidden world operating under a whole different set of rules.
In a way, yeah. And perhaps one of the biggest head scratchers is this idea of wave-particle duality. It's this wild concept that things we think of as particles, like those tiny electrons, can also behave like waves.
Okay, see, that's where I need a little help wrapping my brain around it. How can something be both a particle, like this tiny speck of something, and a wave, something that spreads out at the same time? It just seems, I don't know, counterintuitive.
It definitely goes against our everyday intuition, right? That's part of what makes quantum physics so mind-bending.
Yeah.
But think about light for a second. You usually picture as a wave, right? But it also acts like a particle, the photon. And here's the kicker. It's not just light and electrons. Even objects we can see and touch, theoretically, have wave-like properties.
Wait, hold on. Are you saying that this table, this microphone, even I have a wavelength?
Technically, yes. But, and this is a big but, the bigger the object, the smaller and less noticeable its wavelengths it becomes. Think of it this way. A grain of sand has a wavelength, but it's so incredibly tiny it might as well not exist. For larger things, like us, it's so small, it's basically irrelevant.
Okay, so these quantum effects, they're happening on a scale that's almost impossible to grasp. But if things are so fuzzy at that level, how can we make any sense of it? Like, it's all about probabilities rather than certainties, right?
Exactly. That's a key difference between the quantum world and our everyday experiences. In classical physics, we talk about precise predictions. But in quantum mechanics, instead of saying the electron is here, we say it has a high probability of being here.
So instead of knowing for sure, it's more like what? Playing the odds, but with subatomic particles.
You got it. And the way we figure out those odds is through something called the wave function. Now, before you run for the hills thinking about complex equations, imagine the wave function like a heat map. The hotter a spot on the map, the higher the probability of finding our electron there.
So the wave function is like a probability map telling us where a particle is most likely to be, like where it's more likely to pop up.
Exactly. It's less about pinpointing an exact location and more about understanding the likelihood of different outcomes. It's kind of like trying to predict the weather. We use probabilities to understand the chance of rain or sunshine, but we can't always say for sure exactly when and where those things will happen.
That's a great analogy. So we've gone from a world of certainty to a world of maybe.
Precisely. Embrace the uncertainty. It's part of what makes quantum physics so fascinating.
Yeah.
But don't mistake this for complete randomness. There are still rules and patterns at play, even if they're not the kind we're used to in our day-to-day lives.
Okay, so you were about to explain the measurement problem and how, like, just observing something at the quantum level might actually change what's happening. That's some next-level mind-bending stuff right there.
Yeah.
How do we even begin to unpack that?
Yeah, it's definitely a head-scratcher.
Yeah.
And it really gets at the heart of what makes quantum physics so challenging, but also so exciting.
Right.
It forces us to really question our basic assumptions about how the world works. One of the sources used a really helpful example talking about a single photon passing through a polarizer, kind of like what you'd find in sunglasses.
So before we even get to measuring anything, can we talk about what it means for a photon to be polarized in the first place?
Good point. Imagine light waves, right? They're kind of vibrating in every direction you can imagine. Now, a polarizer is like a filter. It only lets light through that's vibrating in one specific direction, say vertically. And here's where it gets really wild. Before we actually measure it, the photon, it doesn't have a definite polarization. It's in this state called superposition, meaning it's both horizontally and vertically polarized at the same time.
Hold on, wait. It's both at the same time? So it's not that we just don't know which way it's polarized. It's like it hasn't actually decided yet?
Exactly. It's like it's in this fuzzy, undefined state, embracing both possibilities all at once. But, and here's the kicker, the act of actually measuring the photon's polarization, it forces it to choose one state or the other.
So by trying to observe it, by making it interact with our measuring device, we're actually changing its reality.
Okay, yeah, that is messing with my head a bit.
It's a concept that even, like, Einstein struggled with. He famously said, God does not play dice with the universe. He wasn't too keen on this whole idea of uncertainty at the heart of quantum mechanics, but the most common explanation for this whole thing, it's called the Copenhagen interpretation.
Okay, so what does the Copenhagen interpretation tell us about this whole measurement problem?
Basically, it says that until we actually measure a quantum system, it doesn't have definite properties. Those properties, they only become fixed once we interact with the system through measurement. This is like that thought experiment, Schrodinger's cat. Oh, right, with the cat in the box. I've always loved that one, though I'm not sure love is the right word, maybe. Anyway, but yeah, it illustrates this whole thing perfectly, right?
Totally. So the Copenhagen interpretation would say that until we actually open that box, the cat is in this superposition of states. It's both alive and dead at the same time. It's only when we observe it that the cat's fate is sealed.
I mean, this is where it starts to feel less like science and more like some kind of deep philosophical debate, you know? Are we really saying that reality is only what we observe it to be?
Well, that's the million-dollar question. It's definitely sparked a lot of debate among physicists, to say the least. The Copenhagen interpretation, while it's widely accepted, it's not without its critics. There are other interpretations out there.
Like what kind of alternatives? What else could be going on here?
One of the more mind-blowing ones is the many worlds interpretation. It suggests that every time a measurement happens, every possible outcome actually branches off, creating a whole new universe. So, going back to Schrodinger's cat, there would be one universe where the cat lives and another where, well, it doesn't. We just happen to only observe one of those outcomes. But all the possibilities, they still exist somewhere out there in this vast multiverse.
Whoa, okay, that is a lot to take in. So it's not that reality collapses into a single outcome. It's more like there are infinite realities all playing out different possibilities all the time. I think I need a minute to process that one. But are there any other explanations that are a bit more grounded in our, like, everyday understanding of the universe?
There's the hidden variables theory, which basically says there are underlying factors at play that we just don't fully understand yet. These hidden variables, they already determine the outcome of these quantum events. The randomness we see, it's just because we're missing a piece of the puzzle.
So it's not that the photon doesn't have a definite polarization until we measure it, but there's something else, something we haven't discovered yet, that was dictating that polarization all along.
Yeah, exactly. Like if you flip a coin, we think it's random whether it lands on heads or tails, but maybe there's a hidden mechanism inside the coin itself that's actually deciding the outcome, you
Yeah.
know? We just can't see it.
Okay, I can see how that makes a bit more sense, at least from our classical physics way of thinking. But it doesn't seem like there's one definitive answer to this measurement problem. It's like the quantum world is holding on to its secrets for now.
Pretty much. Even with all the research and debate, the measurement problem is still a huge mystery in quantum physics. All the different interpretations, they have their own pros and cons, their supporters and their critics. But for now, the Copenhagen interpretation, it's still the most widely accepted way to think about the strangeness of quantum mechanics.
I've got to say, even without a definitive answer, exploring this whole measurement problem thing has been a wild ride. It's amazing how quantum physics forces us to confront our most basic assumptions about, like, reality itself. It's like we're getting a peek behind the curtain of the universe, and it's way stranger and more wondrous than we ever imagined.
And we're only scratching the surface. These quantum mysteries, they have implications that go way beyond these theoretical debates. They could revolutionize how we process information, communicate securely, maybe even understand the very fabric of reality itself. But maybe we'll save those explorations for another time.
You've definitely piqued my interest. This whole deep dive has been absolutely fascinating. Ready to jump into some of the more practical applications of this mind-bending science.
That's about it.
All right, so after that deep dive into the measurement problem, I'm ready to see how these quantum mysteries actually play out in the real world. You mentioned revolutionizing information processing, right? What does that even look like?
Imagine, like, computers that can solve incredibly complex problems in the blink of an eye. Problems that would take our best computers today, like, millions of years to figure out. That's the potential of quantum computing.
Okay, that sounds seriously next level. But how does quantum physics actually change the game when it comes to computing power?
It's all about the building blocks. Our current computers, they use bits, right? Think of them like tiny switches, either on or off, representing 1 or 0. But quantum computers, they use something called qubits.
Qubits. Okay, I've heard the term, but how are they different from regular bits?
Picture a coin spinning in the air,
Yeah.
right? Not heads or tails yet, just spinning. That in-between state, that's kind of like superposition, and it's what qubits tap into.
So instead of just being a 1 or a 0, a qubit can be both at the same time. That's where the real power comes in.
Exactly. It's like being able to explore tons of possibilities all at once. Let me try an analogy. Imagine searching for a specific grain of sand on a beach. A normal computer, it has to look at each grain one by one. But a quantum computer, it can analyze all of them simultaneously, way faster.
Wow, okay, yeah, that's a game changer. Especially for really complex problems. One of the sources mentioned cryptography. What's the connection between quantum physics and, codes and cybersecurity?
It's a big one. A lot of our online security right now, it relies on the fact that it's really hard for computers to factor really big numbers.
Hmm.
Like finding the prime numbers that multiply together to make a giant number. It takes a long time, even for powerful computers.
But you're saying quantum computers could do that much faster, breaking the encryption we rely on.
They could, yeah. Because they can explore so many possibilities at once, factoring those huge numbers becomes way easier. It's a double-edged sword.
So a potential cybersecurity nightmare, but also maybe a revolution in code breaking.
Yeah, kind of. But remember, quantum physics, it's not all problems. It also gives us solutions.
Okay, good, because I was about to have a panic attack. What kind of solutions are we talking about?
Well, one of your sources mentioned quantum key distribution. It's a way to share encryption keys that's basically unbreakable, using, you guessed it, quantum mechanics. Imagine a communication channel where someone trying to eavesdrop, it would be instantly obvious. The act of listening in would actually change things.
So unbreakable codes, not just something you see in spy movies.
It's a real possibility, and it's being researched right now. Quantum key distribution could change how we communicate securely, especially since we rely so much on digital information these days.
This whole deep dive has been incredible. I feel like my brain is like 3 times bigger. But honestly, I'm a bit intimidated by all this.
That's the thing about quantum physics, right? It makes us rethink everything we thought we knew. But like one of your sources said, it doesn't have to be rocket science. It's complex. But with a little curiosity, it's a fascinating world to explore.
Absolutely. And for our listeners, if you want to go even deeper, definitely check out the sources we used. You won't regret it.
It's a field that rewards curiosity, that's for sure. Who knows what other mysteries are waiting for us in the quantum realm?
Well, that's a perfect note to end on. Thank you all so much for joining us on this journey into the quantum world. Until next time, keep those minds curious and stay strange.